What's our geometric view of differential equations? Well, it's something that's contrasted with the usual procedures by which you solve things, you know, and find elementary functions which solve them. I'll call that the analytic method. So on the one hand, we have the analytic ideas in which you write down explicitly the equation y prime equals f of x y, and you look for certain functions which are called its solutions. Now, so there's the ODE, and y1 of x, notice I don't use a separate letter, I don't use G or H or something like that for the solution, because the letters multiply so quickly, that is, like rabbits, multiply in the sense of rabbits, that after a while, if you keep using different letters for each new idea, you can't figure out what you're talking about. So I'll use y1 means it's a solution of this differential equation. Of course, the differential equation has many solutions containing an arbitrary constant. So we'll call this a solution. Now, the geometric view guy that corresponds to this version of writing the equation is something called a direction field. And the solution is, from the geometric point of view, something called an integral curve. So let me explain, if you don't know what the direction field is. I know for some. So what's a direction field? Well, a direction field is you take the plane, and at each point of the plane, of course that's an impossibility, but you pick some points of the plane, you draw what's called a little line element. So there's a point, it's a little line, and the only thing which distinguishes it outside of its position in the plane, so here's the point xy at which we're drawing this line element, is its slope. And what is its slope? Its slope is to be f of xy. And now you fill up the plane with these things until you're tired of putting them in. So I'm going to get tired pretty quickly, so I don't know. Let's not make them all go the same way. That sort of seems cheating. Here, how about, there's a few randomly chosen line elements that I put in, and I put in the slopes at random since I didn't have any particular differential equation in mind. Now, the integral curve, so those are the line elements, and the integral curve is a curve which goes through the plane and at every point is tangent to the line element there. So this is the integral curve. Hey, wait a minute, it's not tangent to the line element there, it didn't even touch it. Well, I can't fill up the plane with line elements. Here, at this point, there was a line element, which I didn't bother drawing in, and it was tangent to that. Same thing over here, if I drew the line element here, I would find that the curve had exactly the right slope there. So, so the point is, the integral, what distinguishes the integral curve is that everywhere it has the direction, that's the way I'll indicate that it's tangent, has the direction of the field everywhere at all points. At all points on the curve, of course. Where it doesn't go, it doesn't have any mission to fulfill. Now, I say that this integral curve is the graph of the solution to the differential equation. In other words, the differential, writing down analytically the differential equation is the same geometrically as drawing this direction field, and solving analytically for a solution of the differential equation is the same thing as geometrically drawing an integral curve.